All right, folks. So today we're going to talk about some extensions to logistic regression. Just as a review, the stuff we've talked about with logistic regression, it's a type of regression that we can think about in three separate spaces. So we could have it in the log odds space where it is linear, we could have it in the odds space where the equation is e to the all that stuff, or we could have it in the probability space, which is where we have e to the all that stuff over 1 plus e to the all that stuff. And just generally in this class, we spent a lot of time thinking about quantitative response variable and doing linear regression. First simple linear regression, then multiple linear regression. And then we've been thinking about using a binary categorical variable as our response, and that's for logistic regression. So we've thought, again, about simple logistic regression and then multiple logistic regression. Now we are going to pretty quickly do two extensions to logistic regression. One is multinomial logistic regression, and that is an extension of logistic regression where our response variable is an unordered categorical variable that has more than two possibilities. So it has 3 or 4. You probably wouldn't want to go like more than 5 categories because it's going to get really hard to understand, but it has more than 2 categories. And then there's ordinal logistic regression, which is when you have a categorical variable that has a natural ordering to it. So it has more than 2 levels, but they have a natural order to them. For both these examples, I'm going to use the diabetes data from the book that you read from. So we're going to think about these people, they're patients, so you can see the patient number there, and I've just taken a random sample from the data so you can see a few of the patients. I've got patient 14, patient 50, patient 118, etc. And then we got variables like relative weight, their insulin response, their steady state plasma glucose, and then their clinical classification, CC, which could be normal, meaning the person doesn't have diabetes, could be chemical diabetes, which is kind of like the first stage into diabetes, and then overt diabetes, which is the more serious clinical classification. So I'm going to talk to you about multinomial logistic regression. This is the one where you have an unordered factor where there's more than 2 levels, and we're going to use this multinomial regression, sometimes also called polytomous regression. And for this one, we need to pick a base level or a reference level. We'd call that level K, and then our model is going to be the probability of being in group J, some other group, compared to the probability of being in group K. So you can see the right-hand side of this equation looks pretty normal. It's the left-hand side that looks a little bit different. Instead of having pi over 1 minus pi, we have the probability of J over the probability of K. So if we think about this with our diabetes data, I've fit this diabetes model using R, and then I have some output. And the output looks a little different than we're used to. So this section right here is the part that we're focusing on right now. These are the coefficients. And what it does is it gives me one line for the chemical diabetic and one line for the overt diabetic. And with each one, I get an intercept, and then I get a coefficient for SSPG and a coefficient for IR. And I could use those to write out my models. So this is the logit of the probability of being a chemical diabetic compared to being in the normal clinical classification, and then here's my equation. Or I could make the equation for the logit of being an overt diabetic compared to not having diabetes, and here's the equation here. So I'm just reading off these coefficients, I've rounded a little bit, and I've written it out as the model in the log odds space. Just like with logistic regression, I could then, exponentiate it, and then I could, do all those other sorts of things to move it into the different spaces. But here we are in the log odds space. So one of the ways that we might want to use our model would be to do some interpretation. And so on this page, I've exponentiated my coefficients so that they are odds ratios, just like I would do for regular logistic regression. And then I have my recipe sentence here. It's very similar. So we've got our 1 unit increase in our explanatory variable, we've got the odds, but now we're saying the odds of comparison group compared to the reference group. and then they're multiplied by a factor of the odds ratio, and then that is the odds increase or decrease. And of course, if we had a categorical variable, we'd have to do our compared to, and then the odds are higher or lower, but we're gonna stick to quantitative variables for right now. So if I wanted to interpret this coefficient right here, this 1.019, which I've rounded to 1.02, I could say for a 1 unit increase in SSPG, the odds of chemical diabetes compared to having a normal clinical classification are multiplied by a factor of 1.02. That is the odds increase. I could do the same thing for the overt diabetic. For a 1 unit increase in SSPG, the odds of overt diabetes compared to that normal clinical classification are multiplied by a factor of 1.04. That is the odds increase. So we don't have the comparison between chemical diabetes and overt diabetes, although the book has a way to make that comparison. But in this case, the coefficients that we get, they're specifically referring to that reference category in our response. So that's the new thing, is we have reference categories in our response variable rather than just in our explanatory variables. And I can do the same thing for the IR, for a 1 unit increase in plasma insulin during the test, then the odds are multiplied by 1.003. And I said the odds stay about the same because that didn't seem like a very big change, multiplying by 1.003, not a huge amount bigger. And the same idea, so for overt diabetes compared to normal clinical classification, the 1 unit increase in plasma insulin makes the odds multiplied by a factor of 0.99. And again, that is the odds stay about the same. So again, the interpretations are pretty similar to normal old logistic regression, but we just have more categories in our response. So that table didn't automatically give us test statistics or p-values. So we had this section that we were focusing on with the coefficients, but we don't see any p-values, we don't see any asterisks telling us significance. But we also have this section of standard errors, so we can find our test statistics and p-values pretty easily. So for example, if I wanted to know if the coefficient for SSPG was significant for the chemical diabetes compared to normal clinical classification, I could take my beta for SSPG, beta hat, and divide it by the standard error for the beta hat of SSPG. And in this case, that would be the 0.0195 divided by, and then I go find the standard error for that coefficient, 0.00445, let's say. And if I do that arithmetic, it is 4.38. And in this case, I would probably just compare to a normal distribution, and I would just use the facts that I have memorized about the normal distribution. I know that anything that is greater than 1.96 or less than negative 1.96 is going to be significant. 4.38 would be like way out in the tails. So I think this is significant. I think that SSPG is a significant predictor of the odds of having chemical diabetes compared to being normal. Let's do one. Maybe let's do this one because this one has a negative coefficient. So we'll do the IR coefficient for the overt diabetes compared to the normal clinical classification. So I'll do my beta hat for IR over the standard error for my beta hat for IR. And in this case, it's going to be negative 0.0134, let's say, divided by 0.00465. And that's about 2.88. So it seems like it's significant, but it's not as significant, right? It's getting closer. Oh, should be negative there. So I took my negative sign off, but yeah, it would be over here, just a little bit more negative. So it looks like it's a significant predictor, but not as significant. We could also do confidence intervals, and we just want to see if our confidence interval crosses a critical value. So if we were in the log odd space, we'd want to see if that interval crossed 0. And if we were in the odd space, we want to know if it crosses 1. So again, I've exponentiated here just because I like thinking about odds ratios, and it looks like SSPG for the chemical diabetes, that whole 95% confidence interval is above 1. So, we're 95% confident that the odds ratio is between 1.01 and 1.03, let's say. Not a huge odds ratio, but it's all on one side of 1. Versus the one for IR, that one crosses 1, so we don't think that's necessarily significant. And then if we go down and look at SSPG for overt diabetes, we've got 1.03 to 1.06, let's say, for SSPG. And I'm looking at this EE plus 00. That means I don't have to do anything with my decimals. But this one right here, it says E minus 0.1. So that means it's actually 0.977 here. And so this interval is 0.97 or 98. We could round to 0.99. So it's really getting close to crossing 1, but it's not quite there. So again, maybe significant, significant, significant. This one is not significant. Okay, so that was about multinomial logistic regression. But what if we have an ordinal response variable? That is a categorical variable that has a natural ordering to it. So in our diabetes example, we probably shouldn't have used that clinical classification as a normal categorical variable because it has a natural order to it. Doctors usually see people go from like being in the normal classification to classifying as having chemical diabetes, and then if their diabetes gets more severe, then that's called an overt diabetic. And so probably we shouldn't have used multinomial logistic regression, we should use ordinal logistic regression. And I've just got a little bit of R code here because when you look at the levels of a categorical variable, it will show you, what the options are. And R will always put them in an order, but there's something called an ordered factor. And if you look here, I ask, is it ordered? Originally, false. No, it's not. And so I do a little bit of data wrangling. I turn it into an ordered factor variable. When I look at the levels, they look the same. It's still normal chemical diabetic, overt diabetic, normal chemical overt. But when I ask, is it ordered, it says it's true. And so that's just giving R a little bit more information about this variable, that it should be considered as an ordered categorical variable. And if we were going to do ordinal logistic regression, it's like a little bit more different from standard logistic regression, because instead of comparing the probability of the reference group and then a comparison group, we're going to compare the probability of the reference level to all the other comparison groups in order. So we're going to say, what's the probability that the value of the response is less than a certain level? So less than having chemical diabetes, less than having overt diabetes. And then we're going to look at the logit for that probability of being less than a certain level of that categorical variable. This is called a cumulative logit because you're going to look sort of cumulatively, everything that's below a certain level. So if we run ordinal logistic regression on our diabetes data, now that I've turned CC into an ordered factor, I get this kind of output. And so the table might look a little bit more familiar. Now I have a coefficients table, and that table has the value of the coefficient. It also has the standard error, and it has the t-value. And again, we could sort of ballpark and look at some p-value equivalents based on those t-values. So this kind of looks like a standard table. And then we have this other piece down here where we have the intercepts. And the intercepts are showing, what the comparisons are that we're looking at. And again, we've got values for those coefficients, standard errors, and t-values. So this is the model that they found in the book. I think the coefficients might be swapped, like they might have the other sign for each of those numbers. And that's just because of the way that R calculates things versus, I forget what software they were using in the book. So if I want to say that we're looking for the probability that your clinical classification is, normal or less, then here's the equation. I have my intercept, and then I always subtract off my coefficients. So if it's a negative, I'm going to subtract off the negative. And then for less than or equal to chemical diabetic, then here we go. So my coefficients on SSPG and IR are the same, it's just the intercept that's different between those two groups. And because this model is pretty different, we're going to have like a fairly different interpretation. So at the top here, I have just used the Broom package to tidy up my model. So now I have all my estimates in a column, all my standard errors, all my t-statistics, I have my coefficient type, and then here I've exponentiated all my coefficients. So these are odds ratios. And again, we have sort of a standard recipe sentence for a 1-unit increase in the explanatory variable, the odds of being more likely to have sort of like more success, that is like the higher comparison groups as opposed to being like the reference group, are multiplied by a factor of the odds ratio. And again, the odds increase or decrease. So here's the example. For a 1-unit increase of SSPG, the odds of being more likely to have diabetes, that means having chemical or overt diabetes as opposed to being normal, are multiplied by a factor of 1.03. That is, the odds increase because that odds ratio is greater than 1. And for a 1-unit increase in IR, the odds of being more likely to have diabetes, chemical or overt diabetes, as opposed to that normal clinical classification, multiplied by a factor of 0.996, that is, the odds decrease. All right. Again, we might want to do some inference. Typically, we wouldn't find p-values for this kind of model because we don't have a good distributional approximation. So instead, we'd make a confidence interval and see if it crosses a critical value. Again, that's 0 if we're in the log odd space or 1 in the odd space. I've exponentiated here, so I am in the odd space, and I want to see if these intervals cross 1, and they don't. This one is all above 1, and this one is all below 1, so we're pretty confident that those are good coefficients. Another kind of inference that we might want to do is to compare to the null model. So in this case, that would be the model that just has an intercept compared to this more complex one. And I've done a likelihood ratio test, and I've done it in increasing order of complexity. So then when I look at this p-value, I'm saying compared to the null model, is the larger model better? And that p-value says yes, it is. So the larger model is better. It's doing a better job of explaining the deviances. And then, of course, there's conditions for inference. For the ordinal logistic regression model, one of the most important conditions is the proportional odds assumption. It's sometimes also called the parallel regression assumption. And the way that you test for this is using this thing called the Brant test. So I can look at the output from my R, and it's really handy. It just gives you the output and says whether that assumption holds or doesn't hold, and in this case it does. So I should be good to go there.